Hello everyone, my name is Samer El Haj Mahmoud and I am joined here by my colleague Gilbert Chen. We are from the Arm Architecture and Technology Group, and today we are presenting an effort to standardize the Arm servers sideband management interface. So let me start by talking about Arm server management standards, and the main specification that we have is the SBMR, or the server-based manageability requirements. The SBMR is a specification published on developer.arm.com. It outlines hardware and firmware requirements for standardizing system management for ARM servers, and it builds upon industry standards from DMTF, OCP, and IPMI. The goal of SBMR is to help the server ecosystem to standardize the foundation based on industry standards and provide common manageability functions and to the users that expect those functions to match what is available today in the industry as capabilities for system management. It still allows partners to innovate on top of that foundation of standards. The control plane of the server has been a strong requirement from ARM data center and hyperscale ecosystem, and use cases include monitoring, sensor and platform telemetry, RAS and error event logging, firmware management that includes update and configuration, OS deployment, and even remote debugging through the BMC. If you are familiar with the ARM System Ready program, that's an umbrella program for certification compliance of ARM systems. It's built on top of ARM standard specifications, the SBSA, BSA, BBR, to name a few. Those ARM specifications are themselves based on the ARM architecture as well as industry standards from various industry standard organizations, and they enable an ecosystem of software just works on the ARM servers. Similarly, SBMR leverages industry standards for instance, DMTF to build standard manageability capabilities using either commercial BMC firmware from firmware vendors or OpenBMC open source firmware. This diagram shows the high-level architecture of SBMR. The main two components that we describe are the ARM server SoC and the BMC chip, the base management controller. You have interfaces between those two subsystems. You have also interfaces from the BMC to I/O devices like PCI adapters on the system, as well as to platform elements like power supplies, fans, sensors, flash devices. And then you have interfaces that are exposed to the end user, either remotely through out-of-band management or from the OS running on the host through in-band management or host interfaces. The SBMR, along with the other ARM server standards, are developed in an industry consortium called the ARM System Architecture Advisory Committee. The consortium uses facilities like Mantis and Causeway to collaborate in writing those specifications and making all the changes to those specs. There are many companies across the ARM ecosystem, from silicon providers to OS vendors, OEMs, software and firmware vendors that work together to establish these standards. A high-level overview of the SBMR specification is that we divided the spec into compliance levels, starting with M0 being the minimum of it's mostly implementation defined with maybe some IPMI functionality, and moving through the levels, moving higher in compliance and in functionality, including introducing some standard interfaces, and then moving to more advanced interfaces, deprecating legacy interfaces. For example, moving from slower bandwidth to higher bandwidth interfaces, We don't have time to cover all of this in today's presentation. We are going to focus, as seen in this architectural diagram, on the sideband interface, which is the interface between the BMC and the satellite management controller, or the SAT-MC component in the ARM server SoC. That interface is used for telemetry and sensor reading between the two subsystems, so the BMC can collect power, thermal events, error logs from the ARM server SoC and make them available to the users through the BMC out-of-band interfaces. Now you may ask, what is the satellite management controller? That's an entity we define as a microcontroller or a processor. It could be integrated in the ARM server SoC or a discrete part outside, and it has a dedicated management interface, a sideband interface to the BMC. So it offloads a lot of the management data transport to the BMC. And typical use cases include sending, like I mentioned, the telemetry and temperature and power data, RAS error logging, and even the boot progress codes. In the Level M3 SBMR, we standardize that interface to be the physical medium being I2C or a higher bandwidth interface, for example, I3C, with the transport protocol being MCTP with PLDM data types on top of the MCTP transport protocol. A quick overview of our journey so far. The first release of SBMR was out in March of 2020. It had levels M0 to M2, level M3 and M4 were in alpha preview. Over time, we introduced SBMR 1.1 earlier this year with some errata and some clarifications and a new functionality. And now we're working on the next major revision, which is 2.0. And the main focus on 2.0 is around the standardization of the sideband interface, as well as more concrete use cases and flows using MCTP for management. Now, my colleague Gilbert is going to go over the implementation and the proof of concept for the SBMR sideband interface. Gilbert?
Yes, thanks, Simon. And the slide will show the our POC for SBMR Level 3 sideband interface. For the SAT-MC, we choose the Arduino Due. That is a single board computer available on the market. And for the BMC, we use from the ASPEED AST2600 EVB board. And the interface for sideband for level 3 is I2C. So the picture shows how we connect the I2C interface in between the two boards. Next slide, please. Yeah, next slide. Thank you. And the software for BMC, of course, we choose the OpenBMC. Is a very popular OpenBMC solution. And with that, in additional library to support PLDM and MCTP, of course, we need a lib MCTP and PLDM library. And application, we use an esteemed application, PLDM tool or MCTP BMC web service to handle the out-of-band command. And SAT-MC, the OS, we choose the Zephyr RTOS, and with the additional library, lib MCTP and PLDM, that's integrated from the BMC to the Zephyr OS. And application, we implement the MCTP and PLDM command responder to handle the command from the BMC. Yeah, next slide. And the diagram shows how the firmware component interacted together to handle the out-of-band management request, like a Redfish, fetch the data from the SAT-MC. From the beginning, end user can send a Redfish command request to fetch the sensor info as exported by the SAT-MC. And then BMC receive a request and get the information by dbus from the PLDM sensor service. And PLDM service will, once he received a request, he was converted to the PLDM command, like the get a sensor reading, send a command through the MCTP demands and ASPEED driver, and then to the SystemArch itself, and the SystemArch firmware will respond the data back to the PLDM sensor. But how the message was can be delivered correctly to the SystemArch is the information. The PLDM header has a EID or sensor ID, those information to let the under layer to route in the message. Those information is provided by entity manager, and the entity manager is coding the data provided by PLDM device. PLDM device will get the full data, also using a PLDM command sent to the PLDM SystemArch response, get a response through data, and entity manager using the full data to match is a database to choose which JSON config file should be used for the SystemArch, and then the PLDM sensor can get know how many sensors in the SystemArch have, and how to has a knowledge to access the SystemArch. Yeah, next slide. And the slide shows some of the design concept assumption for the MCTP layer. We assume the SystemArch has a one for each MCU or CPU or SoC, and if the system is a multiple CPU, then all the SystemArch is on the same ASPEED bus, and the SystemArch we assume is a non-ARP capable device, and that means the ASPEED address is fixed and based on the circuit number. Those assumptions makes the hardware requirement and firmware design as simple as possible, easy to implement, because now all the ASPEED controllers support the broadcast ASPEED address. And we assume the circuit number has a mapping ASPEED address. And with those assumptions, it can simplify the MCTP ASPEED discovery procedure. BMC just need to simply scan the ASPEED address range, and once he receives acknowledgement from the end device, he can send a set endpoint command to set the EID MCTP EID to the each SystemArch. Next slide. Yes, thanks. And the slide shows some design decision for the PLDM layer. PLDM specification describes two access models. One is a PLDM command for the access sensor data only. Another is a PLDM with PDR. Not only PLDM command not only get the sensor data, but also read provide how many sensor loss sensor configuration data, like the threshold value, sensor unity or sensor type. The sensor is a numerical or static. For the PLC, we implement PLDM access only. With this model, and SystemArch need to implement the full data command for the BMC to fetch the full data, and the SystemArch need to implement the full record PDR. Let the up layer to know the SystemArch support the full data, and the full data is available in the for this SystemArch, and then the BMC get the full data and compare to the entity manager JSON file database, and then like the previous slide showed, and then the PLDM sensor, the daemon know how to has enough knowledge to access the SystemArch. Next slide. Okay. And the flowchart describe each component, how the PLDM or NCT command are sent by each service to the SystemArch, and to accomplishment the task for end user to access the SystemArch by the output bay interface. First of all, NCT daemon need to discover how many SystemArch in the system. So he will run through the MCTP discovery procedure. And then after that done, the PLDM device will issue the get routing table entry to know the EID list, and PLDM device using the PID list to fetch send the get a PDR repository command, get a PDR and get a flu data record. Those PLDM command to get a flu data for the entity manager to know and then provide the necessary information for PLDM sensor to access the ZNC. Next slide, thank you. And then PLDM get enough information from the entity manager service, and then he can try to start initialize the ZNC, like issue the TID command, and set a event receiver, and set a sensor threshold, and set a sensor enablement command. Those necessary command to initialize the ZNC sensor. And then the PLDM can move to the polling phase. And every time the polling event occurs, then he can get a sensor reading command to fetch the latest reading to for the upper layer, like the BNC web. Next slide, thank you. And the example, the slide shows the example. User can log into OpenBMC SSH terminal and run the CLI command PLDM tool to send the PLDM command and get a response directory. The example show we can issue the get a TID command or get a status sensor reading command, and the screenshot show the response for your reference. Next slide, thank you. And the example show the user from the remote terminal and use the curl command to send a Redfish request to get a core temperature that's exported by the ZNC. According to the response command, we can get all the information we need for the sensor, like the threshold setting or the current reading. Yeah, next slide, thank you. And the code change, the slide show how many code changes we made for the POC. First of all, of course, we have a BNC, debug sensor, and entity manager, MCTP, and PLDM, and Zephyr, and ZNC. And those code changes currently is available on the GitHub, and with the link shown on the slide. Next slide, thank you. And the next step for the PLC, because we got the information about OpenBMC for the MCTP stack implementation. Currently, the MCTP stack is implemented in the user space. They have planned to move to the kernel space. So the change we made for the PLDM sensor and PLDM device need to do some modification to adapt to the new MCTP implementation. Next slide, thank you. And the slide show what's a to-do list for the PLC. First of all, we have mentioned that PLDM has two kind of access model. One is access only, another is PDR. Then with loss change, we don't need to maintain too many JSON config for each ZNC. And we also plan to implement event message log. And of course, with loss code change, our goal is to upstream back to the community. The first is a safe project. We will try to, we are working on the upstream code change we made, like the I2C target mode driver or MCTP endpoint driver. For BNC, of course, there's many report has a code change we need to submit. The debug sensor, entity manager, and debug MCTP, PLDM, and OpenBMC. And currently, we are working on the upstream the debug sensor code change. And after done, we'll do the following on project. Yeah, that's all the presentation today. Thanks everyone to join the session.